Hello, this is Professor Kitch, and welcome to this webcast on Section 12.9. This is the second of two webcasts covering laboratory shear strength tests. This presentation is on the triaxial test. When you finish this presentation, you should be able to describe the boundary conditions for the unconfined compression test, sketch the setup for a triaxial test and show the applied loads and stresses, as well as draw a free body diagram of a soil specimen during testing. And finally, given data from a triaxial test, you should be able to plot the appropriate Mohr circles and determine the strength parameters phi and c. This is a picture of a typical triaxial test. The specimen being tested is located in the triaxial cell and enclosed in a flexible membrane. The triaxial cell is placed in a load frame. The purpose of the load frame is to apply a vertical load to the specimen. This load is measured by a load cell located near the top of the load frame. Tubing connects the cell to pressure and volume control modules, which are used to regulate and measure the pressure within the cell as well as control the drainage of pore fluid out of the specimen. A computer data acquisition system controls the test and records the data. Now let's take a closer look at the triaxial cell itself. This figure illustrates the triaxial cell and explains how it applies stresses to the soil and how it controls drainage conditions. The specimen sits on a pedestal inside the cell with a loading cap on top. It is surrounded by an impermeable latex membrane that separates the soil and its pore fluid from the fluid that fills the cell. There are two pressure gauges attached to the cell. One measures the pressure of the fluid within the cell, and one measures the pore pressure within the specimen itself. There is a valve which controls drainage within the specimen. The valve can either be closed, thereby preventing drainage, or open, which allows for drainage. A loading piston on top of the cell allows an axial force to be applied to the soil specimen. A dial gauge attached to the top of this specimen lets us measure the vertical deformation. There are two distinct phases in any triaxial test. The first phase is the consolidation phase, during which cell pressure is increased. This provides a uniform confining stress all around the specimen equal to the minor principal stress, sigma 3. During this phase, the soil may be allowed to consolidate or not, depending on the type of test being performed. The second phase of the test is the shear phase. During this phase, a load is applied to the piston at the top of the cell. This load increases the stress at the top of the specimen. Since there are no shear stresses on either the top or the sides of the specimen, these are principal planes. The major principal stress, sigma 1, is applied to the top of the specimen, and the cell pressure provides the minor principal stress, sigma 3, to the sides of the specimen. The vertical stress is gradually increased until the specimen fails. This is a relatively simple schematic of a triaxial cell. Actual cells are more complicated and have additional drainage lines. However, this schematic covers the essential components of a triaxial cell. In actual lab testing, there is a phase that precedes the consolidation phase. This preceding phase is the saturation phase. It's critical during the test that the soil be 100% saturated, and the details of getting a specimen to 100% saturation are an important part of the testing. However, for purposes of our discussion, we'll simply assume that the specimen is at 100% saturation before consolidation. There are several different types of triaxial tests. The different tests are distinguished by the drainage conditions applied during the consolidation and shear phases of the test. In phase 1, pressure is added to the water surrounding the specimen, providing a confining and consolidation stress. During the consolidation, the drainage valve may either be open, allowing drainage, or closed, creating an undrained condition. If the valve is closed, we call the test unconsolidated and use the letter U to label this phase. Since the specimen is saturated at the start of the consolidation phase, there can be no change in the volume of the specimen when the valve is closed, and excess pore pressures will be generated during this phase. If the valve is open, the specimen is free to drain, and we call this phase consolidated and use the letter C to label it. In this case, the soil will be allowed to change volume, and all excess pore pressures will be dissipated by the end of the consolidation phase. During phase 2, the shear phase, again, the drainage valve may either be open or closed. If the valve is open, we call the phase drained and use the letter D as a label. In a drain test, the assumption is that there are no excess pore pressures generated during shearing. To ensure this is the case, we must run the test very slowly so that any pore pressures that might be generated during shearing have time to dissipate. This is particularly important for clay soils which have a low hydraulic conductivity. If we close the drainage valve during the shear phase, we have an undrained test represented by the symbol U. There will be no volume change in the specimen in this case, and consequently shear-induced pore pressures will be generated. We commonly measure the pore pressures generated during shear. This allows us to compute the effective stress within the specimen. We use a two-letter designation to identify the different types of triaxial tests. The first letter specifies the drainage conditions during the consolidation phase, and the second letter specifies the drainage conditions during the shear phase. The UU test is an unconsolidated undrained test. In this test, the drainage valve is always closed. This is a total stress test and does not usually entail measuring the pore pressures. It's also called a Q or quick test since we do not have to wait for consolidation, nor do we have to wait for drainage during the shear phase. The CD test is a consolidated drain test. In this test, the drainage valve is always open. This is an effective stress test since no excess pore pressures are allowed to accumulate. It's also called an S or slow test since we have to wait for consolidation to be completed during phase 1 and we have to shear the specimen slowly during phase 2 so that no excess pore pressures are generated. The CU test is a consolidated undrained test. In this test, the drainage valve is open during consolidation but closed during shear. It's also called an R test, presumably because it's faster than an S test but slower than a Q test. During shear, we normally measure the pore pressures generated. This allows us to compute both the total and effective stresses during shear. Finally, we sometimes perform an unconfined compression test on cohesive soils. Strictly speaking, this test is not a triaxial test. It's not performed in a triaxial cell. It's a simple compression test without any consolidation or any confining pressure. It's similar to an unconfined compression test on a concrete cylinder. Since the test is not performed in a triaxial cell, we have no control over the drainage conditions. In this test, we shear the soil very quickly and assume that there's no drainage. This test is equivalent to a UU test with sigma 3 equal to 0. In the next part of this webcast, we will examine the stress paths followed in each of the 4 tests we just discussed. In each case, we'll present a schematic of the specimen on the left side showing the boundary conditions and the applied stress. On the right, we'll draw the Mohr circles for the tests, plot the failure envelope, and determine the strength parameters phi and c. In the unconfined compression test, a vertical stress is applied to the soil without any lateral confining stress. That is, the minor principal stress, sigma 3, is equal to 0. Therefore, the Mohr circle for this test are all tangent to the tau axis. The vertical stress is then increased until the soil fails. At failure, the maximum principal stress is denoted sigma 1f, or simply called sigma 1 at failure. This is a total stress test. We have no measure of the pore pressures, and we cannot determine the effective stresses in the soil. The peak shear stress at failure is a measure of the undrained strength, SU. There is no failure envelope for the unconfined compression test since we have only one Mohr circle in this test. The UU test is another total stress test. Like the unconfined compression test, we do not measure pore pressures and do not compute effective stresses. The purpose of the UU test is to determine the undrained shear strength, SU. The drainage valve is closed throughout the UU test. Initially, there is no stress on the specimen, and the Mohr circle appears as a point at the origin of the Mohr-Coulomb diagram. As we apply the cell pressure during the consolidation phase, the Mohr circle remains a point because sigma 1 and sigma 3 are both equal to the cell pressure. However, the Mohr circle moves to the right along the sigma axis as the cell pressure increases. Once the consolidation phase is complete, The shear phase starts by increasing the vertical stress applied to the specimen. The minor principal stress sigma 3 does not change as we shear the specimen. We continue to increase the vertical stress until the specimen fails. Again, the maximum principal stress at failure is sigma 1F, and the soil has an undrained strength SU. Because the drainage valve was closed during the consolidation phase, no consolidation occurred, and the soil did not gain any strength during this phase. Therefore, the undrained strength under confining stress is no greater than the undrained strength measured by an unconfined compression test of the same soil as shown here. Similarly, if we conduct another test on an identical specimen, but raise sigma 3 during the consolidation to the point shown, the soil still would not gain any strength because no consolidation is allowed. This third test would also have the same undrained strength as the two previous tests. If we plot the total stress failure envelope for the test, it will have zero slope and intersect the tau axis at SU. This is known as the phi equals 0 condition. Saturated clays loaded in undrained conditions fail under phi equals 0 conditions. Now let's consider the consolidated drained or CD test. In this test, the drainage valve remains open during both the consolidation and shear phases, and any excess pore pressures that might be generated are allowed to dissipate, so there's no excess pore pressure. Therefore, the effective stress and the total stress are equal. This is an effective stress test. During consolidation, the Mohr circle again moves from a point at the origin to a point at the consolidation stress sigma 3. But in this case, sigma 3 is an effective consolidation stress because there are no pore pressures and the soil will consolidate and increase in strength. Sigma 1 is then increased until the soil fails. But in this test, the shearing is done so slowly that no pore pressures are generated. Therefore, the major principal stress at failure is also an effective stress. If we test a second specimen, but consolidate it to a higher confining stress, the soil will gain strength during the consolidation process. When it is sheared, it will have a larger Mohr circle at failure as shown. Likewise, if we run a third test at yet a higher confining stress, again the soil will consolidate and have an even larger Mohr circle at failure. Using the three failure circles shown, we can plot the failure envelope as the line tangent to the circles and compute the friction angle phi prime and cohesion C prime. In this case, this will be an effective stress failure envelope, and phi and C will be effective stress parameters as noted by the use of the prime symbol. Let's look at our final test, the CU test, or consolidated undrained test. In this test, the drainage valve is open while the confining stress is applied and remains open until the soil is consolidated and all pore pressures are dissipated. The drainage valve is then closed, creating an undrained condition for the shear phase of the test, and we will be measuring any excess pore pressures that are generated during shear. The vertical stress is then increased until the soil fails. Since we are measuring pore pressures during the test, we know the change in pore pressure at failure, delta U. Knowing both the total stresses and the pore pressure at failure, we can compute the effective stresses at failure and plot the effective stress Mohr circle shown here with dashed lines. This circle is offset from the total stress circle by a value of delta U. In this case, we have a negative excess pore pressure, so the effective stress is greater than the total stress, shifting the Mohr circle to the right. As in previous tests, we can test a second specimen at a higher consolidation stress. We can then shear this specimen until it fails and determine the total stress circle at failure for the specimen. Again, we'll know the pore pressures at failure, so we can also plot the effective stress circle at failure, here shown with dashed lines. Finally, we can test a third specimen at a higher confining stress, and we will obtain another set of total and effective stress circles at failure. We now have two sets of failure circles. The solid circles represent total stresses at failure, and the dashed circles represent the effective stresses at failure. If we consider just the effective stress circles, we can plot the effective stress failure envelope and determine the strength parameters phi' and C'. Therefore, from a CU test with pore pressure measurements, we can determine the effective stress strength parameters even though the shear phase is in an undrained condition. So now that we've covered the basic triaxial tests, let's discuss some of the advantages this test has over the direct shear test. The triaxial testing procedure gives us control over drainage conditions both during consolidation and shear. Therefore, it allows us to measure either the drain strength or the undrained strength of a soil. The shear plane is not confined to a fixed plane as it is in the direct shear test. This gives us a more realistic failure surface and a better measure of the strength of a soil. The boundary conditions are controlled and known. This allows us to plot complete Mohr circles and determine the stresses on the failure plane. Finally, we can measure both axial and volumetric strains during the test, which allows us to measure the stress-strain properties of the soil. So let's summarize. The triaxial test has the following characteristics. The test is relatively difficult and time-consuming to run, with the exception of the UU test, which can be run very quickly. However, both the CD and CU tests must be run very slowly so that shear-induced pore pressures can dissipate or equilibrate throughout the specimen. The data is more difficult to analyze than the direct shear data, but at the same time we get much better information from these tests. Finally, the strength parameters measured in the triaxial test are more accurate than those measured in the direct shear test. You should now review the learning objectives for this presentation. If you don't feel you've achieved these objectives, now would be a good time to review the presentation. Example 1210 in your text presents data from a CU test. You should review this example before class.
Eso es todo, amigos.